Welcome back. In the previous video I talked about why decision trees overfits the data and why overfitting is a problem. Now in this video I will talk about some techniques to overcome this problem, which is known as regularization in machine learning. So for decision trees there are basically two approaches to avoid overfitting. The first is the early stop, and the second approach is called post-pruning approach. Now what we do in the early stop, I will talk first about the early stop and then talk about the post-pruning. So what we do in the early stop is that, we start growing our decision tree like that. And what we do is that at each stage we consider if a condition is fulfilled. So we want to know if a given condition is satisfied. So if this condition is satisfied, then we grow, or we split the data in a given node. Otherwise we just stop growing the decision tree. Of course there are many conditions, and one of the most important condition is called the information gain. The information gain. So how does this technique work? Well, let's say that for example at this node, right, and I want to know if it is a good idea to split it into two leaves. Well, to answer this question I need to evaluate the information gain. Now what I do is that I consider that I have already done this splitting. I consider, well, I say if I split this node I would get two leaves. Now in that case what is the information gain? And the information gain is calculated as the impurity of this node minus the impurity of this node multiplied by its weight plus the impurity of this node multiplied by its weight. And in this case, in the case of the information gain, the impurity metric that we use is not the Gini metric that I already discussed in a previous video, but rather we use the entropy metric. Okay, now the information gain Ig is equal to the entropy of the original subset. So in this case the original subset, let's say that it's here because I'm considering just whether I should divide the subset in this node or no. So it's equal to the entropy in the original subset minus the summation of the entropy of the subset in this node, right, which should be of course weighted. Therefore I need to multiply that by SV divided by S plus of course the entropy of this node multiplied by its weight. So this summation in my case would be from 1 to n. In my case n is equal to 2. Why? Because I have here two nodes, right? Therefore I have n equal to 2. Now what I say is if Ig, or if the information gain, is higher than a given threshold, ITH, then split the node into two subsets. Otherwise I just stop growing my decision tree. Now I want just to give you the formula of the entropy. So the entropy is equal to the summation, or minus the summation of probability of a given class multiplied by the second log of the probability of the same class. And I, well, let me name this J because I've already used I here. This would be J. So J starts from 1 to m, and m is the number of classes. Now this is just one condition to stop my decision tree. I can define, of course, other conditions. I can say stop the decision tree if the number of samples in a given subset is smaller than a threshold, for example 2. So in that case I can say stop growing the decision tree because it's not really important to divide two samples. This number is very small, so it's not really, I don't see any use in dividing a small number, a sample that has a small number of samples, right? And it is also possible to define a condition that is related with the number of nodes. I can stop the decision tree once the number of nodes reaches, for example, 10 nodes. And the same thing can be done on the depth. Well, the idea is that there are many other conditions that we can use to define when the growing of the decision tree would stop. So this was for the approach of early stop. Now we will talk about the post-pruning approach. And I will particularly talk about a technique that is called the reduced error pruning. Well, to understand this approach, let's first visualize the accuracy with respect of the number of nodes. Well, in practice, this is what happens when we do that. If I want to measure the accuracy with respect to the number of nodes, the accuracy of classification with respect to the number of nodes in my decision tree, this is what would happen. When the number of nodes decreases, then the accuracy would decrease. But the thing is that this is true only on the training dataset. So this line here in green represents the training dataset, or the result of the accuracy on the training dataset. Now, what if I want to represent the same curve, but instead of testing the training dataset, I want to test a different dataset that is called the test dataset. And I will represent it with this color. This would be the test dataset, which is of course different than the training dataset. Well, what happens is that when I decrease the number of nodes, the accuracy surprisingly increases, and after that, after a given point, the accuracy starts to decrease again. And for this reason, one approach or the technique of the reduced error pruning is that we'll let the decision tree fits the data as perfectly as it can, and then we reduce the number of nodes, and for every iteration what we do is that we measure the accuracy, and at the end we take the number of nodes that is associated with the highest accuracy. For example, let's say that the number of nodes here is 15, then I say, well, my decision tree would contain only 15 nodes. That is, I have my original decision tree with the largest number of nodes, and then I start to reduce the number of nodes until I get only 15 nodes, and I say, well, this is the best model that would not overfit my data points or my test data, my test data set. And in practice it was found that usually the approach of post-pruning performs better than the approach of early stop. And this is probably because this approach is based on an empirical evidence, because our choice of 15 here is based on something empirical. This is probably why this approach performs better.